Hello, my name is Sarah Oliva, and my team was Christian Ramirez, Madison Dranbauer, and Ricky Butty, and together we analyzed an Earth albedo modification system with sulfur dioxide, as well as the feasibility of a near-term demonstration and validation of the system. Our corporate sponsor was Dr. Robert Limpert from the RAND Corporation, and our faculty advisor was Dr. Donahue from George Mason University. Today, I hope to go through the concept definition all the way to the recommendation, and this includes the problem. So to start off with the concept definition, one of the largest issues our world is facing today is the rising global temperature. In the past 100 years, the global average temperature has risen approximately 0.7 degrees Celsius and is predicted to rise another 2 to 6 degrees in the next century. According to NASA's Goddard Institute for Space Studies, the 10 warmest years in the past 134 years have all occurred since the year 2000, and the year 2015 is ranked as the warmest on record. What you see here are the temperatures at ground and water surface between the years of 1979 and 2011. This data was collected by the National Oceanic and Atmospheric Administration, and the software is one from NASA called Panoply Data Viewer. Now, what you can note is that there are huge changes in the temperatures, both in the northern hemisphere as well as the equator. The more red an area is, the more significantly affected it has been by rising global temperatures. Another issue that we are facing is the rising sea levels. As of January 2016, the sea level has been recorded as 74.5 millimeters, but it is important to note that these numbers are very conservative as of late studies. Studies have shown that these predictions from current models can be 1 to 3 feet lower than what is actually expected. So sea level rise is actually a very dangerous trend that's happening that needs to be addressed and is not being addressed. So we are referring to albedo modification, but it's important to understand what albedo really is. Sunlight is the primary driver of Earth's climate and weather, and albedo is the measure of the reflectivity of the Earth's surface. As the reflectivity decreases, the temperature then increases. What's important to note is that there are some factors that affect the reflectivity of the Earth's surface, and this includes carbon dioxide. CO2 is majorly contributing to climate change, and the levels in the air are the highest in the past 650,000 years. The excessive amount of carbon dioxide traps rays that are reflected out of the Earth and release a portion of the heat back to the Earth. The rise in global carbon dioxide levels is primarily contributed by greenhouse gas emissions from countries such as China, India, as well as the United States. The current level as of January 2016 is 404 parts per million. To put that into perspective, what you can see here is CO2 levels from the past 400,000 years until present time. This data was collected again by the National Oceanic and Atmospheric Administration using ice core data, and as you can see, CO2 levels had not increased over 300 parts per million until the pre-industrial age. Once that occurred, we skyrocketed up into the current level at 400 parts per million. It's important to note that there have been attempts politically to address the carbon dioxide levels, but as you will see, they have been unsuccessful. There have been 4 major political climate conferences addressing greenhouse gases. The first being the Kyoto Protocol in 1997. This was the first greenhouse gas emission reduction treaty, but only included developed countries. So it did not include China or India, which are 2 of the main contributors to CO2 emissions, and the United States did not ratify that treaty as well. So no change was really coming out of the Kyoto Protocol. Then came the Copenhagen Accord in 2009, and that summit collapsed. No legally binding commitments for reducing carbon dioxide emissions were made, but they had agreed to meet at the Durban conference that took place in 2011. In this conference, there was an agreement to come up with a universal legal climate change agreement no later than 2015, which occurred in Paris in November 30th of 2015. In this conference, it was agreed on a target of 2 degrees Celsius above pre-industrial temperatures, although no binding agreements were made. As of now, we are 1.5 degrees above this pre-industrial temperature, so we're looking to reduce the increase of 0.5 degrees. So the problem is, if carbon dioxide emissions are not stabilized through international regulations, the world may encounter an environmental tipping point affecting most of the world's population. The need is for a modification or maintenance system to be implemented worldwide in order to modify the Earth's albedo and stabilize global temperatures and sea levels if political action does not work. So why is sulfur dioxide being recommended? Because it replicates volcano eruptions. What you can see here is a simulation of the eruption of Mount Pinatubo by NASA. The particles from Mount Pinatubo, due to its location, spread all across the globe and reduced the temperature about 0.8 degrees Celsius from current temperatures. The volcano eruptions release a massive amount of sulfur dioxide into the atmosphere, and these are converted into aerosols. Those aerosols have a residency time of 1 to 2 years in the stratosphere. There have been large drops in the temperatures after large volcanic eruptions, such as Mount Pinatubo and Mount Toba, and these are hoped to be replicated by this system. It's important to note that there are many unknown risks, as well as known risks of sulfur dioxide dispersion. The benefits include the cooling of the global temperatures, the stopping of the melting of sea and land-based ice, slowing sea level rise, and increasing the planet's ability to sequester greenhouse gases. But the risks are many, and some include the substantial ozone depletion, the regional drought, ocean acidification, and the possibility of sky color change, as well as reduction in sunlight. These risks are only a few and show how dangerous this system can be if implemented. In order to address these risks, we recommend a demonstration and validation of the system before any implementation takes place. It's recommended that a proposal for a demonstration and validation be made for cost, benefit, and hazard data and should occur 5 years before implementation. To discuss the scope of this analysis, we'll go over the objectives, the assumptions, the exclusions, constraints, as well as the scope definition. The objective of this system will be to inject sulfur dioxide into the stratosphere to reduce the global temperature. The assumptions are that at least some nations will comply, the coalition of nations will fund the system, and this system will only be implemented after political action fails. It will exclude political impacts, adverse environmental impacts, and the constraints include the residency time of sulfur dioxide in the stratosphere, the location for operations, and the time, funding, and schedule. The scope definition is made up of the preliminary cost analysis, implementation design, and the recommendation of the demonstration and validation. What you see here is a stakeholder tension diagram. These stakeholders are made up of humanity, international governance, national governments, manufacturers, and agencies. Sulfur dioxide manufacturers and aircraft and flight manufacturers will benefit from this system as it will produce jobs. The industrial agencies and environmental agencies will both be adversely affected. The industrial agencies will have carbon dioxide emission caps and reduction goals that they would have to adhere to, and environmental agencies will be concerned about the environmental impacts this system can cause. In international governance, you see United Nations. This is one possibility of the governance of this system, but is most likely not going to agree to back such a system. An alternative to that would be a poor country coalition, and ultimately that would be a cartel of near equator countries that could be paid to not stop once the system is established. The system requirements include mission requirements, functional requirements, as well as the design requirements. The mission requirements include that the system shall stabilize the global temperatures to below 2 degrees Celsius above pre-industrial temperatures for the next 100 years. These systems shall also reduce the trend of rising sea level. For functional requirements, the system shall deliver a certain amount of sulfur dioxide into the stratosphere every phase, and the system shall deliver sulfur dioxide in a defined time period. The system shall deliver sulfur dioxide at an altitude of 10 to 20 kilometers. This is the location of the stratosphere. The design requirement includes that the system shall operate out of airfield bases of operations located around the equator. Now we will talk about the concept of operations. The concept of operations includes buying used commercial aircraft for deployment of sulfur dioxide. These aircrafts will be stripped of all the seats inside and modified to be a cargo plane. They will be refurbished planes to be high-altitude crop dusters. The aircraft will not be pressurized, and thus the cyclical fatigue stresses should be less of a risk than commercial passenger service requirements. As for the sulfur dioxide containers, there are two types, the cylinder and ton container. The ton container will ultimately be the optimal choice as it has the most net weight and will allow more sulfur dioxide to be carried per sortie of aircrafts. There will be 63 to 74 ton containers of sulfur dioxide per plane. Each plane will conduct 5 sorties a day, and the dispersal rate of the sulfur dioxide will be 0.22 pounds per meter. This will give the optimal particle size of the sulfur dioxide to have the longest residency time in the stratosphere. The utilization rate of the aircraft will be 0.65, as each will conduct an hour-and-a-half sortie and have 2 hours for fuel and loading. Maintenance time will also be 9 hours a day. What you can see here are the amounts of sulfur dioxide to be delivered and will be simulated in this project. 1 million tons to 20 million tons are being considered to exhaust all options. 20 million tons was the amount that Mount Pinatubo erupted, but as that is such a large amount, we test smaller numbers to see what is effective. The operational scenario is a single base dispersion. From the operational base, the flight will pick up the payload, fuel, and take off. It will cruise at a latitude between 30 degrees north and 30 degrees south in the location of the stratosphere, and then descend back to the operational base. This will happen 5 times a day for an hour-and-a-half sortie and 2 hours for fuel unloading. The locations for the bases will take place between countries along the equator. This again is the area with the lowest albedo, and the global winds will aid in the east-west dispersal. So the air bases could potentially be in Colombia, Somalia, Brazil, or Indonesia, anywhere that is along the equator to help disperse the particles all around the globe. Now for the method of analysis, which includes the simulation and modeling portion. The utility function used in this system is made up of efficacy, rapidity, and safety. Efficacy is then further broken down into a realistic emissions cap, stabilizing global temperatures, and stabilizing sea level rise. Rapidity is broken down into a mitigation rate and an emergency stop. The model used in this project is called MAGIC, and it is the model for the assessment of greenhouse gas-induced climate change. The creator is Tom M.L. Wigley, and the software used for this project is 5.3 version 2. This software was developed primarily with funding from the United States Environmental Protection Agency and is one of the primary models used by Intergovernmental Panel on Climate Change since 1990 to produce projections of future global mean temperature and sea level rise. The upwelling diffusion energy balance model that produces global and hemispheric mean temperature output together with results for oceanic thermal expansion was used to determine global mean temperatures and sea level rise predictions. The limitation of this model is that there are predefined scenarios which reduce the flexibility, and it is also complex to modify the input files. The first equation that's behind this model is a simple global average energy balance equation. It calculates the global mean radiative forcing at the top of the troposphere. The energy influx is partitioned into increased outgoing energy flux and heat content changes in the ocean. The energy flux is dependent on the global mean feedback factor and the surface temperature perturbation. The second equation behind the model calculates climate sensitivity. The steady-state response of the global mean near surface temperature to an increase in greenhouse gas concentrations is defined by the equilibrium climate sensitivity. It is the measure of the sensitivity of the climate system to external forces. Climate sensitivity is measured in units of degrees Celsius and is inversely related to the feedback factor, lambda. Here what you see is the structure behind the MAGIC software. It starts with a library of emission scenarios. This is where we manipulated the input files to reflect the injections of 1, 5, 10, and 20 million tons of sulfur dioxide a year. These input files go into the gas cycle model. Where you see the user choices of model parameters is where we set the climate sensitivity to 1.5, 3, and 4.5. This was to reflect the variability in climate sensitivity, and again to exhaust all options of what the future climate sensitivity could be. This then goes into the global mean temperature and sea level model and outputs the temperature and sea levels predicted. Here is a sample input file of a scenario of a political cap on CO2 emissions of 450 parts per million and the injections of 5 million tons of sulfur dioxide annually. The implementation would start in the year 2030, which is why you can see the big jump in sulfur dioxide from 4.5 to 29.3. The additional inputs that were not manipulated are seen on the right side of the screen, and these remain the same, unlike the sulfur dioxide amount as well as the fossil fuel CO2 count and the deforestation CO2 count. Here is a sample output data that shows past and current as well as future predictions on temperature and sea level. To verify and validate the data that was gathered by MAGIC, it was plotted against NASA's annual temperature mean and the 5-year temperature mean, and as you can see follows a similar trend, which gives us confidence in the data that the model provides. Now for the design of experiment. 3 inputs were modified: the carbon dioxide cap, including no cap on CO2 emissions, the sulfur dioxide amount, which included no injections of sulfur dioxide, as well as 1, 5, 10, and 20 million tons, and a climate sensitivity of 1.5, 3, and 4.5 degrees Celsius. The CO2 caps also include a cap of 450 parts per million, 550 parts per million, 650, and 750 parts per million. Now, current predictions are that the climate sensitivity will be approximately 3 degrees Celsius, so that's what we'll be focused on in this presentation. Here is the design of experiment for no cap with sulfur dioxide injections of 1 to 20 and focusing on the climate sensitivity of 3 degrees Celsius. As you can see, in the year 2060, even with 10 million tons, we are at about 2 degrees Celsius at 1.8, and then we surpass 2 degrees Celsius in 2100 in all scenarios of injections. What you can see here is the temperature change with no cap on carbon dioxide emissions and no injections of sulfur dioxide, as well as the injections of 1 to 20 million tons. Even with 20 million tons, again, we surpassed that 2 degrees Celsius that was set by the Paris Conference by the year 2080, and the increase is exponential, meaning it is not going to stabilize and will further increase dramatically. This is the sea level change with no political cap and sulfur dioxide injections. Again, these are conservative numbers, but sea level rise can go all the way up to 54 centimeters of an increase from pre-industrial sea levels. Here what you can see is the temperature change with carbon dioxide emission cap of 450 parts per million and sulfur dioxide injections. This is a very optimistic carbon dioxide cap, as we are already at 404 parts per million, and political will has shown to be unsuccessful. But what you can note is that it does remain under 2 degrees Celsius if carbon dioxide is addressed very fast. Even with 1 million tons, you can see that the gradient is going up towards that 2 degrees Celsius, and with 20 million tons, it is stabilizing. But it still gives us below that target number and is the optimal scenario here where we are not surpassing the 2 degrees Celsius. Here is the sea level change with the cap of 450 parts per million, and as you can see, there's a dramatic difference between the 54 centimeters with no cap to the 36 centimeters with a 450 cap. Moving on to the temperature change with carbon dioxide emissions cap of 550 parts per million and sulfur dioxide injections. With injecting 1 million tons of sulfur dioxide, we surpass that 2 degrees Celsius at around 2100. 5 million tons does keep us below that 2 degrees Celsius, but as you can see, by 2130 is about to hit that mark. Only with 10 and 20 do we remain under 2 degrees and shows a possibility of stabilization under that goal. The sea level change with the cap of 550 parts per million shows more of an increase from 450, but still less than no cap at 43.6 centimeter increase from pre-industrial sea levels, and that's with injecting 1 million tons a year. By injecting 20 million tons, we reach that 31, which is just slightly less than the 450 cap with 1 million tons of sulfur dioxide a year. Now for the temperature change with carbon dioxide emissions cap of 650 parts per million and sulfur dioxide injections, the injections of 1, 5, and 10 million tons still surpass the 2 degrees target by 2130. The only injection amount that keeps it below the 2 degrees Celsius is the 20 million tons, but still does not look to be stabilizing and could still further increase above that 2 degree mark. This means that immediate change must be made to the carbon dioxide emissions, as even with 20 million tons, we are not seeing the goals that we need to reach. Here's the sea level change with the cap of 650 parts per million and the injections of sulfur dioxide. And again, these are very conservative numbers, but reach as high as 47.8 centimeters above pre-industrial sea level, and with 20 million tons is still 35.7 centimeters above pre-industrial sea levels. So after a utility analysis was conducted, including efficacy, safety, and rapidity, capping CO2 emissions at 550 parts per million and injecting 5 million tons a year gave the biggest difference with the most amount of safety. 1 million tons proved not to make much of a difference, and although 10 million tons does make a difference, it is less safe than 5 million tons. As safety is one of the biggest goals that are most important to humanity, we swung the weights for this goal, and again, that 5 million tons a year with the 550 cap is the safest goal, as it is the least amount, but makes still an effective mark on global temperatures and sea level. It is important to note that the utility of these isn't the only goal that we are looking at, as this is still a very dangerous system. Now for the cost analysis. Our cost model includes sulfur dioxide acquisition, maintenance costs, personnel costs, the one-time cost of aircraft acquisition, fuel, and operational costs. For the aircraft acquisition cost, the costs are listed for 747-100 to 400, as well as C-17 and 747 Special Performance. The 747 SP and C-17 are omitted from further analysis as the availability is very small, where 747s are more available and also more cost effective. These values are in 2016 United States dollars, and will be focused on 747s from this point on. What you can see are the cost estimations for sulfur dioxide. Each ton is approximately $600 to $700. These are using triangular costs, and these values again are in 2016 dollars. The Monte Carlo annual costs were conducted for each aircraft alternative, as well as every alternative of sulfur dioxide injections. As you can see, the more sulfur dioxide injected, the more money will be needed. This is used with a triangular distribution in 2016 dollars, and again these costs include the sulfur dioxide cost, maintenance, personnel, aircraft acquisition, fuel, and operational costs. Now these costs were plotted with the utility of each of the alternatives in sulfur dioxide, and using a fleet of 747-200s with a cap of 550 parts per million and injecting 5 million tons a year would have the highest utility as well as the lowest cost, and would be the optimal system design if ever implemented. Conducting a 30-year life cycle cost for a fleet of 40 747-200s, dispersing 5 million tons annually, with a projected inflation rate of 2.5% and a discount rate of 6.8%, the expected 30-year life cycle cost is $45.5 billion. For the demonstration and validation estimation cost, for conducting 500 sorties for one 747-200 and dispersing 36,000 tons of sulfur dioxide, the estimated cost is $39 million. The recommendation will be to prepare a demonstration and validation proposal for proof of concept and cost, benefit, and hazard data and analysis. This would be to operate one aircraft out of Hawaii or Guam's United States Air Force Base to deliver 500 sorties for 1 year of sulfur dioxide at the max altitude, and the estimated cost would be less than $50 million. For the consideration of the implementation in 2030 would be to use a homogeneous fleet of 40 747-200s to disperse 5 million tons of sulfur dioxide annually. Again, this is not the recommendation to implement the system, but it is the recommendation to implement a demonstration and validation in order to see the actual results of this system in real life and know if the risks outweigh the benefits. This system implementation would be the fleet of 40 747-200s to disperse the 5 million tons, and each would conduct 5 sorties a day, carrying 72-ton containers per plane. We appreciate your time.